and it seems to be ongoing, which is great. And I think we can wait a couple of minutes, so to start on at 10 or actually at 9.
Good morning, Gerga. How are you?
Good morning. Hey, how are you doing?
Good. Just checking the audio. Good talk yesterday.
Thank you so much.
Impressed with the work you guys are doing.
Thank you. I think the others were giving excellent presentations. You know, it's interesting because we work closely together, but these are these events when you really get to understand like how much was done in even just a short period of time. So I was also very impressed. Thank you.
No, absolutely.
Let me see, people are still joining. So then I will just use these couple of minutes until the start of the poster session to say some housekeeping items. So first of all, for those of you who don't know me, my name is Gergely Zahoranszky-Kőhalmi. I'm the informatics lead of the Aspire program, and I am the moderator of this poster session today, of the informatics poster session. And in this session, we will hear about funding opportunities related to the Aspire program. And also you will get a chance to get a behind the scenes glimpse on the topics of reaction informatics and infrastructure development in Aspire. If you have any questions, then you can also put it in the chat box, or once the talks are over, which will be 15 minutes long, then you can also ask the questions from the presenter. And I will also give a warning basically at the 10 minutes mark, so that the speaker will know that they have 5 minutes to wrap up the talk, because we are on a tight schedule here. So we want to make sure that we are on the spot with the schedule. And with that said, I would like to introduce our first speakers. And please welcome Dr. Dobrila Rudnicki, Doda, who is the program director of the Office of Special Initiatives at NCATS, and also Dr. Sean Gardner, who is the scientific program manager, Office of Special Initiatives at NCATS. And they will talk about the NCATS Aspire program, building unique intramural, extramural collaborations to explore novel biologically relevant chemical space. With that said, Doda, please have the floor.
I think Sean will present, so I'll be here to answer the questions.
Okay.
Well, good morning. Let me share my screen. All right, is the slideshow coming up? There we go.
Okay.
Can you see the slides?
Yes, we can see. And,
okay, there we go.
Please go ahead.
Here on my ends too. All right, well, good morning, everyone. I'm happy to start off this session of the Aspire Day poster session. A big thank you to you, Gergely, for today's introduction, and to reintroduce myself. My name is Sean Gardner. I'm a scientific program manager in the NCATS Office of Special Initiatives. And you've heard yesterday about the amazing work that's being done in the Aspire Intramural Laboratory and the groundbreaking developments that they're making. I'm going to be presenting an update on the extramural side of things of the Aspire program, and let you know about some current funding opportunities that are available and ongoing, and whatever else that we have in the works. But first, a little bit of backgrounds. So this slide / infographic should come as a surprise to no one, as you've heard from Chris this morning. Traditional drug R&D takes a really long time and it's extremely expensive. On average, a decade passes in between a disease target that's been identified, and until that time, a drug has gone through preclinical and clinical design and testing. It takes about $2 billion to get to that point. So despite the great cost behind pharmaceutical R&D, there's still a failure rate of 90%, either due to lack of efficacy or due to toxicological events unforeseen in humans by the time it gets to the clinical stage. From 2010 to 2015, that average cost of drug development per drug has gone up from 1.8 billion to about 2.6 billion. Still takes about 10 years to reach market, and less than 12% of the drugs entering clinical trials result in an approved drug. 90% of known biological space is left undrugged, that Chris had mentioned, and this leaves the door wide open to further discoveries in drug development. But the difficulty lies with the cost and time required to bring a discovery to the point where it can reach market. And a lot of that time in this process is taken up through iterative compound synthesis and testing in order to get the data that we need to further optimize lead drug candidates and to move them into a clinical setting. So anyone who's been a part of traditional medical chemistry, Chris's graphic and slide this morning in the introduction was really great to show that things between 1917 and 2017 really don't look that different. So enter the INSPIRE initiative, which our program's goal is to solve these translational roadblocks by addressing automation, synthetic chemistry, with AI and machine learning, and biological screening. That way we can reduce the iterative data cycle needed in order to make decisions and bring things into a clinical setting in a more efficient fashion. So the ASPIRE initiative is a catalytic transformative drug design and development program, and we want to greatly increase the rate at which we're able to match chemical space with the undrugged biological space. So the available chemical space is about 10 to the 60 potentially active molecules. And the key challenges that we hope to address are to identify those molecules that are going to modulate that 90% of undrugged biological space. So if you'd like to read more about the framework for the ASPIRE program, I encourage you to read that 2019 paper that was put out. There's more information as well about our program on the ASPIRE website. For the extramural side of things, we use funding mechanisms to contribute new technologies and capabilities to this platform through extramural research in collaboration with the Intramural Lab. So a brief timeline that I'll go through quickly. Concept clearance for ASPIRE was in 2017, and following which the automated synthesis workshop that Chris had mentioned took place, in which areas were identified that the ASPIRE program can tackle in order to accelerate drug discovery. The 2018 ASPIRE design challenges were launched using money from HEAL, and following that, a second paper was put out in Frontiers in Robotics and AI in 2020. Following that, we've opened up new challenges and RFAs, which I'm going to go through in just a moment. So as a proof of concept, I'm going to discuss how this all came to be. So initially, in 2018, an NIH-wide initiative launched called HEAL, which called Helping to End Addiction Long Term. And this funding was applied to improve prevention and treatment strategies for pain, opioid use disorder, and addiction. This funding allowed NCATS to launch the initial ASPIRE design challenges in 2018 and solicit the extramural community for innovations in drug development centered around pain management. So, as I previously mentioned, the automated chemical synthesis workshop brought together a consortium of expert chemists and engineers who were interested in automation and some who were not, in order to identify these key areas that could be initially developed in order to accelerate drug development. And those areas are an integrated chemistry database. So we wanted to be able to find out how we can collect the data, chemical, clinical, and biological, that already exists in database. How do we all access it in one place? And how do we access it in a format that's readable for machine learning and AI? The second challenge area is an electronic synthesis chemistry portal. We need to collect chemical data in real time in an unbiased manner, and it's critical to collect negative data as well to devise good AI approaches, as we can learn from things that don't work just as well as we can from things that do work. Improved predictive algorithms. How do we develop algorithms to analyze data from chemical and biological experiments in real time and couple it with the databases to assist with decision-making in the drug development process? The fourth area is biological assays. We would like to develop robust assays that can validate new chemistries and drug candidates, and how to extract usable data from it quickly, be fed back into the database, and be analyzed by algorithms to refine the medicinal chemistry data cycle. And a fifth challenge area was outlined in order to design a way to combine at least two of the designs into an integrated solution to get people how to think to take these individual units and interface them together. So in this competition stage, there was no prototype development. Feasible designs and potential solutions in the different challenge areas were submitted and judged by intramural scientists at NCATS, which provided initial funding to get these ideas off the ground. There were many exciting applications, and a ceremony was held to allow the winners to mingle and discuss possible collaborations for the next challenge stage. So in November 2020, we announced the stage for the challenge, the second stage for the challenges, to build a prototype for a modular solution that incorporates all four of the areas outlined in the previous challenges. Many of the applications that we received were teams that were formed from the collaborations between innovators that participated in the first challenges, though to note, participation in these previous challenges weren't a requirement for entry into the 2020 challenges. A unique feature of the 2020 Aspire Challenge is that we are including the NCATS Aspire Intramural Lab, and they're going to pressure test and validate the physical prototypes of these modular drug development systems that were created by these extramural teams that are participating in these challenges. So this challenge was designed in stages, and at each stage, different milestones need to be reached in order to move on to the next. You can see more details on the website listed below. I will show you a current timeline of the 2020 Aspire Challenge. Stage 1 is the submission of a feasible plan. Stage 2 is the development of a working prototype in which different milestones are completed. We're currently waiting upon the submission of milestone 1 by the end of the summer. And then from there, we're going to move on to the next milestone. And stage 3 is prototype delivery. And the innovators must successfully complete this milestone before a prototype will be accepted. And the NCATS intramural laboratory is going to be independently validating these modular systems. So one grand prize winner will be awarded $750,000, and one runner-up will be awarded $325,000. So these are the winning projects from stage 1 with successfully submitted designs, which were judged by intramural scientists here at NCATS. The other team members and their affiliations, aside from the leads that are listed now, are listed on the website below. And it's important to note that throughout this process, intramural scientists at NCATS are involved in every step as reviewers of the submissions and the materials, to providing their expertise on subject matter expert panels to judge the progress being made at each milestone. And we're really grateful for their time and expertise to help move this challenge forward. And we're also very excited to see the progress that's being made on these modules by the innovators. So in parallel to the current challenge, the Aspire program has released 2 research funding announcements in order to build on the intramural laboratory's capabilities by funding cooperative agreements with extramural research groups. So these collaborative initiatives allow the Aspire intramural laboratory to be a partner with the extramural research groups in the development of these modules. The opportunities are funded through the Cures Acceleration Network, and this opens up the research to include any human condition rather than focusing specifically on pain research. We anticipate the outcome of these RFAs to allow the identification, design, synthesis, and validation of new chemical entities as starting points for novel drug targets, and the expansion of chemical space available for drug screening. So this first funding opportunity is for the development of a physical module to be incorporated into the NCATS Aspire platform by allowing extramural groups to collaborate directly with the intramural lab toward its development. So below are some examples of the physical module types that fit the scope of projects that we're interested, but it's not limited to those. And they're mainly, as you can see, related to synthetic chemistry. Another funding opportunity is for a virtual module to be incorporated into this platform through development with the Aspire Laboratory and their Informatics branch. And modules of interest are listed below. With this RFA comes an opportunity to use cloud-based computing resources and support provided by NCATS to aid in this module's development. So we encourage everyone to send this to your family, your friends, anyone else that you know that would be interested. Here's the timeline for these research funding announcements. Currently, the application due date is by 5 p.m. on July 8th, 2021. So as that approaches, we encourage you to apply and come with any ideas. And please contact either myself or Dota with any ideas that you have, and we'll get you connected with the right people in order to make these ideas and applications come to fruition. So where are we going from here? What do we want to do? We see multiple opportunities to expand this program and facilitate the expansion of the platform in order to make synthetic chemistry more of an information-based, reproducible science. Some areas that we see potential in are incorporation with other NCATS programs and initiatives. Biological assay development could come by interfacing with the Aspire platform with 3D bioprinting and the tissue chip programs. Increasing the amount of accessible chemical space through interfacing AI and machine learning analysis to our natural product libraries. And we can even envision using synthetic biological methods to afford the preparation of small molecules and challenging synthetic transformations in this platform. There's space for collaboration with other federal agencies in order to take advantage of other funding mechanisms to provide innovation, as well as further collaboration with DARPA, which has been fruitful in the past. So far, we've had the challenges, and now we have research funding announcements and cooperative agreements. But we would like to develop initiatives in the small business and startup areas by contributing to that research through SBIR grants and contracts. And finally, while we understand that there aren't a lot of chemists who are interested in automation, but have developed chemistries that are amenable to being automated, we would like to bring in that into the program and expand the capabilities. So I'd like to thank everyone for your time today, and thank you for attending this session. We would like to acknowledge the many people that helped bring the Aspire program to the stage we have it now, and we look forward to working with them to expand it even further. We're in the Office of Special Initiatives, and a big thanks to our Dreamer-in-Chief, Dan Tagle, and to Dota Rudnitsky for all the guidance and information that she provides, as well as the other members of OSI. Thank you, Chris Austin, for your return this morning, and for Joni Rudder for your leadership, and for both of your support for this initiative. So we're very happy to be part of what makes NCATS great. And another thank you to OGMSR, Brent Loomis in the Financial Management Branch, Billy Portilla at the Office of Strategic Alliances, Sam Michael, Alex Godfrey, and all the members of the Aspire Intramural Laboratory for your hard work, big ideas, and the expertise that allows all of this good stuff to happen, as well as our collaborators at DARPA. So I'd like to open the floor to any questions, if you have any. Thank you.
Thank you so much, Sean, for the great talk. And I like to encourage the audience to ask the questions. You can ask it out loud. We have time, like 5 minutes. And also you can put your question into the chat box. And until we receive the first question, I just wanted to again say thank you for this great presentation, because I think this information is something that many people and groups are looking for. And I think it's very informative, it's very useful. Clearly, as yesterday we heard, ASPA is a very collaborative project. So we are looking for all those opportunities. And I have a general question. Like we heard about the challenge prizes, we heard about the RFAs. So I wonder, like on the longer term, like can people hope for more funding opportunities? And also, if let's say somebody will not get funded in these rounds, is there still another way to, what's the best way to collaborate with us? How can they reach out to us, and what mechanisms we have to support those collaborations?
So I can take the question to help Sean. Great talk, Sean. So this is, we're just starting now. And as we heard so many times, this is an extremely ambitious program, and we're looking forward to develop new initiatives. Now, the way we work, we usually develop an initiative and we, excite the scientific area, and then we move to the next one. So there's not really opportunity to resubmit if you're not funded. But you can rest assured that we'll be working very hard to branch out the Aspire to different problems, and that these initiatives will keep coming as the funding becomes available.
I think this is really great news, because I know that this field is really moving fast and there's a lot of interest to contribute to this. I also say extremely exciting project, and also very important. Like I also wondering, let's say if somebody wants to just, write manuscripts on this field, then what is the proper channel to do that? If we would like to look for certain expertise, then does it require some sort of collaborative agreement to initiate, let's say, a collaboration on writing a manuscript on some topics? So can you maybe shed some light on that?
I don't think that it needs to be collaborative agreement. It's just that, as a government, there's certain rules you have to comply with when you're writing, papers with extramural community. But this is all about innovation. So, there shouldn't be boundaries between you and others who are wishing to really advance field through the ideas they wish to publish. So, there's just like some ethical things that you have to follow when you're publishing the paper. But we would strongly encourage any kind of collaboration, whether it's in disseminating, whether it's in thinking what else we need to develop. And again, because this is a completely new field, you would expect that as we go along, we will see additional problems and additional areas that need to be addressed. So this needs to be extremely mobile in the sense that we can quickly then address this area. And NCATS has a great example of tissue chips program that really, invigorated the field and took opportunity of every angle to expand in it and to address and then now disseminate. So the main goal here is to keep interaction between our intramural side and the extramural community. And, as soon as there's an additional angle that we need to address, try to address it and develop this collaboration. And the other main thing is these are not the typical collaborations where you collaborate on the grant and you don't know what's going to come. These are very hands-on collaborations where both sides are very much involved and trying to solve the problems along the way, and hopefully they're going to be very successful. So
thank you so much, Dora, again, and Sean, for the great talk and for the answers. And with that said, I'd like to introduce the next speaker, who is Vishaka Goya, and she's a robotics engineer in the Aspire team at NCATS, and she will be talking about the Internet of Things IoT infrastructure behind the scenes. Vishaka, please take it away.
Thank you, Georgi. Good morning, everyone, and thank you for showing up for this presentation. Today, I will be talking about IoT infrastructure, and I will start with sharing my screen. Okay.
We can see the screen now.
Okay, good. So just a little background. In case you attended yesterday's presentation on our IoT dashboards, you must have learned about what we're actually building here at NCATS. But today's presentation will be more of a deep dive into that dashboard and the engineering details behind it. And also we want to share all of this information with you guys, since we at NCATS, we procured a lot of different licenses and we figured out what all technology will work at NIH and for our lab environment. And we would love to share that with the rest of NIH. So with that, let's get started. So, okay. First about IT at NCATS, just a little recap, why we're doing what we're doing. Our main objective is to put as many laboratory instruments as possible on cloud, so they can be controlled by a single platform by scientists, and they can remotely monitor and control these devices. And also we want the scientists to be able to run proper reaction flows instead of just controlling individual instruments. And in order to do that, we are sharing data between different devices and allowing proper complete reaction flows to be operated from a single dashboard. Now talking about the actual technology behind it and the tools being used. So we are using IT tools from Microsoft. The reason to use these tools by Microsoft was that most of what we're using, they're all plug and play tools. So they need local development and for the most part. And for example, we have IoT Hub. It's an extremely important, this is the main IoT tool from Microsoft. This is the cloud tool where we have all the data storage, analytics, and streaming being routed to. And this is the main cloud platform from Microsoft. Then we have Azure Stack Edge. Now, this was also one of the reasons to go with Microsoft, since this particular piece of hardware is extremely important for us. It enables something called edge computing. If you're not aware of edge computing, it's a concept where you don't have to run everything on cloud. A lot of times you might want to run analytics or storage on premises. And this piece of equipment allows us to package our pieces of code, whether it's to analyze certain information or just to communicate between different devices. We can package all of these pieces of code into Docker containers, and all of that can be run on this one piece of hardware. And this allows us to communicate with multiple different devices, all in parallel. And then again, yesterday there was this question raised about latency issues. So although we haven't seen it yet, but it is possible that you don't want to send all the data to the cloud and run analytics in cloud, since there might be some latency issues between sending that data, streaming that data. In such cases, you can run all of that analytics on edge itself. This is a piece of hardware sitting on our NCATS premises, and it allows storage analytics. And then once you have all this data on cloud, that is your storage or streamed data, whatever it is, next you want to visualize that data. The user obviously wants to see it. The user doesn't care about Stack Edge or IoT Hub. They are just concerned with visualizing what's coming into the user interface. And we are using something called Power Apps for our user interface development, since again, it's a plug and play tool and we didn't really want to build everything from scratch for prototyping. And Power Apps also displays data from Power BI. And Power BI is a data visualization tool where, let's say you have some telemetry information or some data that can be displayed in the form of graphs, so like pressure data. And Power BI allows you as a user to manipulate that data, to mess around with those graphs, figure out what's going on exactly, and all of that is being displayed, collected on Power Apps. So Power Apps gets data from Power BI, and Power Apps also gets data from other sources, which I will be getting into as we progress. So talking about the actual data flow from user interface to our laboratory instruments. So as I mentioned before, we're using Power Apps for data visualization. Now, starting from scratch, when the user wants to interact with any device, they will go into that device page. And let's say you want to start a reaction. Now, what happens is when you enter your reaction parameters as to what you actually want to run, the information about that reaction, then you will obviously press a button to start the reaction. When you press that particular button to start the reaction, what it does is that it triggers Azure functions. Functions are these, again, it's a piece of code, low code environment running on IoT Hub. And this Azure function will in turn trigger our edge modules, which are sitting on the stack edge device. And these modules will in turn trigger our downstream devices. That is, like in our case, we're using HQ Pro. And when you trigger these, so basically, okay, yes. So we have Raspberry Pis right now, which are communicating with the laboratory instruments. And we went with Raspberry Pi because it's good for prototyping. You can use any other microcontroller as well. So the way it works is you have to create device APIs, which we obviously did for each instrument. And in our case, we created them for HQ Pro, and we're also prototyping with BioTouch V10. So all these different devices will use different protocols for communication, like HQ Pro uses TCP/IP protocol and BioTouch V10 uses UDP. And our main goal ultimately is to create abstract APIs. So we have to make minor changes and not create these APIs from scratch for every device. And we are collaborating with other outside companies for such initiatives as well. And so this was about triggering the device. Now, to get the data from device, it's a similar process. The data comes from HQ Pro, goes through Stack Edge to IoT Hub. And if you see here, you see this thing called AMQP. So the way you might be wondering, okay, so I understand that data is coming through TCP/IP, but how is it actually going to edge, and how is the data going from edge to hub? So these, so we're using these Microsoft APIs, which in turn use transport protocols called AMQP. Now, Microsoft provides a bunch of different options like AMQP, MQTT, HTTPS. And for our purpose, AMQP was the best since, as I mentioned earlier, we want our stack edge device to be able to communicate with multiple devices at once. And AMQP is the only protocol out of all these three options, which will allow message multiplexing. And that's why we wanted to go with AMQP. And once you have your data on Hub, now, on IoT Hub, there are a ton of different options to to analyze or to store data. And as you can see here, if you want the data that's being streamed to IoT Hub, the telemetry data to be displayed in the form of graphs, then that can be done through Power BI, and that in turn is displayed on Power Apps. And then if you have some data in the form of log files being stored on IoT Hub, then that can be stored on blob storage. And again, that can be displayed on Power Apps. And then there are a lot of other different options like SQL tables or SharePoint lists. And I mean, there's a whole list of different methods to store that data and visualize it on Power Apps. And that can be done through these premium data connectors, which come with a license of Power Apps. And these data connectors allow us to directly call those lists which are being created on IoT Hub. Now, you might be interested in displaying some third-party information on Power Apps as well. Like in our case, we are displaying information from sources outside of IoT Hub as well. Like we're integrating with Gyoke's platform AICP. So in such cases, you create your custom connectors, and it's again a very simple, straightforward process of creating something called a Swagger file. And it's just, again, low-code process. So you can just create your custom connectors and import that data on Power Apps. So that is pretty much all about the data flow from between the user network and the on-prem network. And of course, when we're talking about data flow, one of the key features is to talk about security. So the benefit of using Microsoft tools is on most ends, Microsoft itself takes care of security. They have inbuilt certificates, and we, even as engineers, don't have to worry about them. But where we have to take care of security, again, this is an entire process explained by Microsoft, that when you have your stack edge device, the data that's being shared between your stack edge device and your cloud, that is already secure because they have inbuilt certificates. But when you want your data to be shared between your stack edge and your laboratory instrument, or in our case, Raspberry Pi, now in that case, you need to bring your own certificates. These are SSL certificates, and they have to match on the downstream device. And by downstream device, I mean Raspberry Pi and the stack edge. If they don't match, the data will not be able to go through to the stack edge, and you can't just send data from any random device. And that's one of the benefits of these certificates to ensure security. So that was about data security during data flow. Now you might be wondering about, as a user, you don't want everyone to be able to see the data that's coming out of your reactions. So in that case, our dashboard application has something called access control enabled. So which basically means that the admin will control which user gets to see which device and which user gets to see what data. So by default, as a user, you won't be able to see anything, and you request for permission for a certain device, and then based on that, you get permission for that for that device. So that is about the security. And if you have any questions, please let us know. So now talking about hardware automation. So even in yesterday's presentation and up until now, we have talked a lot about IoT and using software for automation, but none of that would be possible without hardware automation, because that is what actually ensures a closed loop automated system. So for example, as a user, you should be able to monitor what's happening in the lab. And for that, we are installing cameras. Then there are certain instruments where when you're running a reaction, manual intervention is needed, like whether it's to change a beaker to avoid liquid overflow, or whether it's to just switch different pipes or switch off a valve. I mean, there are all these different small steps where a manual intervention can be needed. And we are trying to get rid of these small interventions, because obviously, we don't want the user to go to the lab for every such thing. And to do that, we are installing sensors like level sensors, then flow sensors. So we are trying to build completely closed loop automated systems. So which will mean that as a user, you can truly monitor and control everything from your desk. And in some cases, we are also incorporating machine learning if level sensors cannot be used, and we want to use cameras to do the same. And in some cases, it is just not possible to automate certain devices if the vendors don't cooperate. I mean, it is possible. So in such cases, we are also exploring benchtop device development, because this will allow us to actually build automated systems according to our needs. And yeah, that's just to highlight how much of hardware automation is also needed along with software development. So I just wanted to show this video because this was shown yesterday, but it just shows the importance of hardware automation as well. Like, this is the screen where you see the reaction running. And if you see here, this video from the camera, it actually enables the user to see what's going on in the lab. And without this, you will obviously not know. I mean, you might get data, but there's no way of knowing for sure that that's actually what's happening. So yeah, that's just what I wanted to show through this video. It has been shown before. So, okay. Now coming to the big picture and where IoT fits into the entire Aspire initiative. So this was shown yesterday, but Megha did not really go into a lot of detail about it. So I will be talking about each of these smaller block diagrams. And Jorge, if you feel that I missed out anything about ASCP, please feel free to correct me. So, okay, now as a user, you get started with your IoT dashboard. You log into your dashboard, and the first thing you want to do is get a list of instruments, access instruments. And that is done through this RSS instrumentation site. So just to give a broader information about it, we have 6 different components, like the Aspire initiative can be broken down into 6 different components, where one is our IoT dashboard, another is the experiment knowledge base and AICB, that is what Jorge's team has been working on. We have chemical inventory, which is something that Alex's team is also working on, and it's about consumables. And then we have instrument inventory, which is Guardian's team, and they're working on this entire list of different devices and information about them, the actual physical instruments. And then we have chemistry activity, which is obviously the real chemistry that's being run. So that's what it can be broken down into. And then the red that you see here, they are the on-prem network, the green is the API, blue is the Azure cloud, and yellow is the NIH network, which is NCATS network in our case. So yeah, as I said, when you want to get a list of devices, that can be accessed through the RSS instrumentation site. That is Carlene's team. They built this entire amazing website where you have this entire list of different devices and information about them. So let's say you want to access a device, but you don't really know how it works. So all of that documentation is also stored on this website, and that can be accessed through something called Device Library API. But to access it, you have to go through something called user access authentication, which will just route you to the NIH authentication. You can't just access the devices without that. So once you have a list of all these different instruments, then obviously the next step is to set up your reaction. In order to set up the reaction, there are a bunch of things that will be needed. So if you see here, you might need obviously the reaction compound, you might need device vessel, and there can be other consumables as well, but these are the ones that are used in almost everything. And then we have reaction parameters. So that is, for example, for HQ Pro, you want to set certain reaction parameters like pressure information or the valve position. So all these things. What you see here in blue, that will be entered on our IoT dashboard. And this is the actual physical consumable. And all of this information is used to set up our reaction. And once you have set up all the information, as I've already explained how the dashboard works. So you will run run your reaction on the dashboard, and it'll communicate through Raspberry Pi and our device APIs, and in turn run the reaction. Now, we have given an example of fractionation purification.
Excuse me, Vishaka, we're within the 5 minutes. Sorry,
can you say that again?
Yeah, we're within the 5 minutes.
Okay, so I will try to, I'll try to accelerate this. So once you have all these reactions set up, you run your reactions, and all of that is being monitored using an IP camera, which is being controlled through a low latency network switch. And also we are recording all that video through something called a DVR. And then we are also collecting all this device reaction parameter into something called an experiment knowledge base, which will in the future serve as an input through reaction templates for AICP. And now on our Power Apps dashboard, we are collecting a lot of information like reaction parameters, as I mentioned earlier, for each reaction. And that is being stored in this thing called scientific metadata storage, which is a combination of the reaction parameters and a combination of the data of some data that's coming from AICP, that's the chemistry information, like catalysts or reaction information, like like the temperature, pressure information. So whatever's needed, all of that is being stored in something called scientific metadata storage, and it's being accessed through AICP from something called Open Reaction API. So this entire thing shows that the dashboard, the IT dashboard, is not just a standalone application which will get data from just the devices, but it will tie into this big picture of Aspire. So for future, we want to add more devices to cloud and create more abstract APIs. And we also obviously want to integrate instrument scheduling, so users can schedule their reactions and as needed based on calendars. And I would like to thank everyone mentioned on this list. And if I missed anyone, I'm really sorry about it. And thank you to this amazing team. And if you have any questions, please let me know.
Thank you so much, Vishaka, and sorry for the interruption. I know these are very tight schedule, and we are all experimenting here, like what is a poster session in these days. So this is it, and we try our best. And if there's any question from the audience, I would like to encourage you to ask it from Vishaka. And in the meantime, I just have a question for you, like Aspire will be an autonomous platform, chemistry platform. Now the question is that will you be able somehow to turn off the autopilot just if there's a need be, so that chemists can remote control? Let's say there's not a workflow that they can execute, but they want to do something custom. So will there be option to manually control, remotely the lab and each instrument as they wish from home, just as if there's a need?
Yes, so we have actually talked about it earlier, like amongst the team, that in such cases, we will have to get rid of the screens that are sitting there. So we would encourage people to use this dashboard even for the runs that you were talking about. So all the data is being collected through the dashboard because it's not always possible that you can run So in HQ, right, if you're running something through the screen, then you can't access it through the dashboard. It's not possible. The communication won't work like that. So yeah, we will get rid of the ability to control, to use those screens, and we will obviously train people to not use them and just use the dashboard that we're creating.
Okay, thank you so much. And I don't see any other questions. So thank you again, Vishaka, and again, excellent talk yesterday too. So again, thank you so much. A lot of progress you guys did in this very short amount of time. With that said, I like to, and just a quick, I think you may have got a question. So I'd like to encourage you to answer that in the chat box. So our next speakers is Bijou Matthew, who is the program manager in Aspire at NCATS, and Chinapong Songchan, who's a software engineer, again, Aspire NCATS, and they will talk about SeeMyLabs, legacy instruments modernization. And Bijou or Chinapong, please take it away.
Yeah, thank you, Gary. So let me first see if I can present it. Can you see my screen?
Not just yet.
Okay. How about now?
Yeah, we'll see it. Thank you.
Okay. Yeah. As you heard from presenters Vishaka and yesterday from Megal, modern instruments are often web-enabled, app-based, wireless, and at times autonomous. Yet many of the instruments used in the laboratories these days are systems of the past, and they therefore do not have such modern features of convenience and automation. I'm Bijou Matthew, and I Aspire program manager. Along with me is Chinapong Songchan, a software and automation engineer. Little over 2 years ago, Sam and Dimitrios tasked us with modernizing a legacy software system used for robotic automation. With the seeds to this project were planted then, it was during the pandemic when the benefits of taking time to modernize our outdated software system truly came to light. During the past year, especially at the times of lockdown, how many of our researchers would have wished for the ability to remotely trigger the experiment, collect the data, and somehow complete their research work all offsite? And this is what we are going to discuss in today's presentation. So TOX21 robotic system, TOX21 robotic system uses a scheduling software called Dispatcher from Wako automation to automate running of assays. For our pilot project, we are trying to modernize this legacy system. Now, for some context, when I say legacy system, I am referring to a system that manage laboratory instrument often built a decade. These are fully functional, great piece of equipment that have become staples in our laboratories, but lack modern web-enabled UIs and running local software to manage automation. They're kind of caught in between, not old enough to warrant replacement, but not new enough to have modern features that would bring them online. As we are looking for a solution to web-enable this system, we came across an industrial SaaS platform that has a capability to integrate both legacy and modern systems. With the foundation, we're able to spin off or create a SeeMyLabs, a cloud-based SaaS product for laboratory instruments, basically digital tuning the legacy instrument, cloud enabling them end-to-end with encryption, and most importantly, a platform that can support legacy protocols like RS-232, Modbus, OPC, Ethernet, to name a few. At this point, I'm inviting Chinapong to discuss TOX21 robotic systems at NCATS, how he created an interface and connected to the SeeMyLabs platform. Chinapong.
Hello. One of the key benefits of Wako Dispatcher is its extendability where it's an ActiveX control API. This allows assays to be launched and monitored externally from custom application created by ActiveX control supported programming environment. There are currently several custom assay launcher applications developed using LabVIEW by Sam Michael and his team. Next slide, please. Biju.
Yeah.
Next slide, please. Okay. Using this benefit, we develop a small custom application using Microsoft.NET technology, utilizing the same dispatcher ActiveX control to work with in conjunction with current existing SA launcher applications. This software monitors transaction messages broadcasting from the dispatcher and create custom JSON status messages for system level information, plate inventory, instrument status, and assay batch information for sending to SeeMyLabs webpage. The SeeMyLabs website engine translates those JSON messages into web-based graphical view, allowing users to log on and monitor system and assay status from outside NCATS networks. This will be safe and secure with the application is running behind the firewall and only send out messages to SeeMyLabs secure webpage. With this, I'll transfer back to Biju for more detail on the SeeMyLabs platform.
Thank you, Chinnapong. As you can see how Chinnapong coded an interface and connected to SeeMyLabs platform. So SeeMyLabs platform system architecture is pretty simple. It includes 6 major modules from edge computing to messaging queue, applying rules on the data, and machine learning. A step that we haven't utilized for this project at this point, but it can be, and a custom UI or a data. As you see, this platform is highly modular. In our proof of concept, we used AWS managed platform, but these modules can very well be developed using G-Cloud or Azure. The input modules receives data from PLCs, sensors, or APIs, which are then encrypted using tokens and streamed via a web server. Streaming modules can be Kafka or AWS Kinesis, and data is then aggregated using Spark on AWS AMR. That's the design here. Data is then stored in the raw format to AWS Glacier for auditing purposes. The data is also stored in Parakeet format, a columnar database storage that saves a lot of data storage and boosts performance. Lastly, an inbuilt inventory administrative tool that enables the management of all instruments and its child devices and establishes grouping of the instruments in the system itself, which will be demonstrated to you in the demo at the end. And also meta information is stored in the AWS DynamoDB and backup to S3, AWS S3. The platform is highly customizable, integrates with both laboratory and business systems. It is ready to deploy with ease. It can support various inputs for easy interfacing. It's highly scalable as it uses AWS managed services, and thus resources can be allocated as demand increases dynamically. Lastly, the data is secure end-to-end, can be accessed via a role-based access control system, and also can be integrated into AD. At this point, I'm going to give a demo on Wako Dispatcher extension to the cloud. As you can see, you can run this application from a web browser using a username and a password in this case, but you can use, can be integrated to SSO. As you see, there's a reward group here, and this group shows all the child devices associated with this, centrifuges, dispensers, filters, etc. And all this can be added and managed using the models, the machines, and the systems, and they can all be grouped or categorized, as you can see, all in this dynamically. And in the monitoring section, we have all the machines, whatever you added, and you can go into each of the machines and see its current status, what it is doing. For example, this one is running a plate and is busy. And there's a live video stream possible. We haven't attached that at this point. And another section in this is the batches, all the batches that have been run so far. Some of them are completed. You can see some of them are still running. I'll show one of them which is completed. The top portion shows all the meta information, as you can see there. And the bottom is all the plates that has been run and how much time it has spent on each of those devices. For example, the centrifuges or the plate readers, how much time it has spent. It's a Gantt chart, time-lapse series Gantt chart. And also there's another tab that it shows all the different devices and the parameters for the method that has been used here for this particular one. As you can see, I'll take back you to another batch which is running now. As you can see, this is the current status. If I refresh, you'll see more plates will be added as it comes in through. You can see dynamically all the changes that is happening to the plates. I'll show you another view from the robotic itself. Look at dispenser 3. When I refresh, it's going to change the status to busy, and the plate is the new plate sitting over there. So this currently shows what's going on in the field. So as we can see, we have extended a locally managed robotic system dispatchers extension into the cloud. And with this, I'll conclude my presentation. I wait for the questions if you have any. You can always reach us at reach back to Sam or myself, Biju Matthew, if you have additional questions there. Thank you all for.
Thank you so much, Biju and Chinapong, for the excellent talk. And I wonder if there's any question from the audience. We have plenty of time. And Biju, I have a question that, so Vishaka mentioned that they are developing interfaces for these devices. So I wonder, when you do the modernization of the legacy hardware, are you making those interfaces compatible with the interfaces that Vishaka and Megav are developing?
Absolutely. I mean, what we are doing in that is, enhancing the capability of our labs, which is, even if it is not there, we are trying to see how we can automate and bring everything to cloud, right? But yet, there are many instruments which are very useful and are very crucial to our laboratory that also need to be brought up to speed, right? So we are trying to bring up those legacy systems. So we found a already ready-made software that we can use. But as Vishaka said, we are also developing, using later technologies like Azure cloud and all that, Persia or all the rest of that's coming through as well.
Thank you so much. And I generally wonder, like, what are the devices that you want to modernize further, and are there any devices that are particularly challenging to modernize?
Right. I mean, we are looking at this way now. At least we should be able to monitor or read at the best. If we can command and control them, that's the next level. So we are tiered it in different ways. So and the third is, you use a very modern system that is already web enabled and all can be controlled remotely. So if they are not, at least we want a ability to see what's happening. So that's why she talked about all the camera things and all that. So you're going to put stage it with all the cameras in the laboratory so we can see all the edge conditions, what's happening on the laboratory level. So that it can be done all safely. That's a prime thing when we automate these kind of things. So everything cannot be automated. There have to be some people, to handle those edge conditions and accidents. Right? It might happen. So, that's the higher level plan. So first level is at least give the ability to see what's happening. Can we schedule it? Can we see what is being used at this point? If we can do that, next level is yesterday Megav talked about, how he is able to control HQ and VTech. That's the next level.
Great, thank you so much, Biju. And Yeah, go ahead. That's a question.
Sorry, I'll just like to add here that to what Biju said that, and to answer your question, I think almost every single device will need some level of modernization. Like we will have to definitely install sensors or cameras on almost all of these devices. So to answer, I think it's not just one, it's most of them that need some extra input in terms of hardware. And there'll be rarely any devices that will be, as Cardine mentioned in the chat, to be automated completely.
Yes, thank you, Vishak. And also, as I said, we have some time. So if to make a little bit more like probably like the more traditional poster session, like I also encourage the audience to ask any of the presenters if you wanted to ask some question that you didn't have time for. We have time. And also, just in case, until we receive those questions, Bijou, I also have a question, like, can you also integrate this interface into the AI CP so that you can also take advantage of the blockchain technology that we developed?
Absolutely, we can do that. As I told you, this particular platform has is highly modular. You can choose which modules you want to use it, and because it's all API driven, each can connect with another, so it can all be integrated.
This is great. That's why we love APIs. They are the glue between these modules, and that's an emphasis that we designing this platform, also the computational platform, but also the hardware platform to be very modular, because at this phase things are moving fast, and at the end of the day we will have a great prototype. It will be still a prototype. So that's the flexibility that the APIs provide, and so that we can make all this integration. Is there any programming language, Bijou, or you mentioned the framework that you use to modernize these legacy devices?
No, I mean, that's why I said, like, this being modular, for example, I showed you the Kafka or AWS Kinesis, you can use either one. So it should be cross-platform, even cross managed services. It could be, some of them could be in GCP, some of them in Azure, and others in. So if it's all API, as you said, very well said, it's a glue. So you glue them together and make it work.
Great. And maybe just a general question also to the IoT team is that you mentioned the microcontrollers. I'm also a big fan as a hobbyist of those, and I'm always happy to see Raspberry Pis. And I also wonder, are there any other microcontrollers you use? I wonder if you tried maybe Pi Zero, and also I wonder, how much problems do you anticipate them in this very special chemistry lab environment when you have different organic solvent vapors?
It depends on the sensor types. Mostly it boils down to the lowest end thing, which is the sensors, right? What it can integrate to very well. If you already have sensors, what can fit to that without replacing it. Otherwise, if we can replace with a modern sensor, it can integrate with any of the modern. It can directly integrate to the cloud also, right? So with Azure, we have seen that. But we are trying to see not replace what is working. We are trying to enhance that. So we have to look at each of those instruments, each of those devices, and see what it fits and what it can integrate to. So it could be Raspberry Pi, or it could be another a higher end, which is a VM with a Docker on that, those kind of things,
Yeah, that's absolutely correct. And I think we have in the past played around with Odroid as well. And yeah, there are just so many options out there. But as Biju said, you can just, at least for prototyping, you can just start with one that is the most popular, because you know that there will be more support for it out there in case you run into some problems. And Raspberry Pi is obviously extremely popular in the IoT world. So yeah, but again, it's dependent on the resources that you have.
Yeah, I think that's very true, and I love exactly that you have such a great community support also for the Raspberry Pi. So it's truly amazing, and also it to me is also fascinating that you can actually use them, as I said, in an organic chemistry lab.
Mm-hmm. Yes, I mean, as Biju said, you have to see which sensors can even be used or not, because it is possible that if you're using a flow sensor and it just breaks down with the liquid that you're using, you don't want that to happen. So you have to be aware of. But the thing is that in chemistry, you can find a lot of such sensors if you work directly with companies that build sensors for such applications.
Yes. Okay, thank you so much again, Vishaka, Biju, and Chinapong. So with that said, I would like to introduce the final speaker of this poster session. And so I'd like to welcome Dr. Chin Shu, who is an informatics scientist at NCATS, and she's contributing to the research of the Aspire Informatics team. And she will be talking about multi-layer reaction knowledge-based development towards retosynthesis. And with that said, Chin, please take it away.
Sure. Thank you so much, Gerge, for the introduction. So let me share my screen. So
Biju, maybe can you stop the screen share? I'm not sure if Chin can take away. Yep. Thank you. Okay. Yes, we see your screen, Chin.
Screen. Okay. So you can see presenter mode, right?
Yes.
So, okay, thank you so much, Gerge, for the introduction. So today I just want to briefly just introduce some of the work we have been done in the NCATS. And the talk I just want to give is multi-layer reaction knowledge-based development towards the retrosynthesis design. So this is like the collaboration with Yuhong Wang and Gerge. So both of them just help on just some of the process of this project. So when we just think about the retrosynthesis design, I think the most critical component coming to our mind is how we can identify the most appropriate directions for the inquiry molecule. And on top of that, we also want to consider some of the critical functional groups. It's just essential to make this reaction happen. So in order to consider all those kind of information, we thought we should just come up some of the a nice reaction data model can just appropriately just present the reaction data we would like to just analyze. So back to 2013, so InfoKing has already come up some of the they call 3-layer reaction model for the reaction classification. So this is a snapshot from this paper. So they just have just come up some of the 3-layer models, which is coming from the reaction center. And as the first layer, they call broad layer. And then they do some of the topological extension. Then they have just from the reaction center, the 1 layer expand out. So they call this is a media layer. And also they have a lateral mirror to have just 2 layers expand out from the reaction center. So by inspiring from this reaction data model, we're thinking, so probably we can do like the similar way and just capture some of the like I mentioned, critical reaction functional groups we can capture in this data model. So then we just design or propose this multi-layer reaction data model. So similarly, we have 3 layers, and the first layer is similar to the InfoKing's model. It's a reaction center. But instead of just only consider the reaction center as a backbone, we also would like to capture some of the rest of those structure be captured as R groups. So that gives us some of the capabilities to do something instead of just only when we match in the reaction, we'll not just only match the reaction center, but also we can consider some of the similarity comparison among these R groups. And moving forward, we'll not just do some of the topologic extension. Instead of that, we just want to capture all those functional groups with the reaction center as a backbone for the second layer. So we proposed to use a maximum common substructure as the backbone of the second layer. And also similarly, the rest of the structure will represent as R group. So the last layer will just include the individual reactions, which is coming from the original resource. So we call individual reaction layer. So review from those reaction center to individual reaction, you can see the reaction backbone is getting more specific reaction, but in another way, you can get some more broad reactions to enlarge the searching space during the ritual synthesis design. So like I see this application, this project right now, we're mainly focused on the ritual synthesis design. So we are just mainly focused on the product, because once the new molecules come in, we just want to do something matching between the product to find whether they have just a appropriate reaction that can be used to do the ritual synthesis. So my talk will mainly focus on the product centralized multi-layer reaction knowledge base for the ritual synthesis design. But once this pathways go through, so that will be easy for us to extend to the reactant, then we can do something reaction prediction later on. So next, I just want to give you just a very brief introduction about this, just the architecture of those this workflow. So, and see how the ritual synthesis application can be designed, or can be developed or built on top of those knowledge base I'm just talking about. So once we have these 3 layers being seated up, so once the inquiry molecule is coming, so ideally we just want to find whether this molecule has been already been synthesized by some of the known reactions. So then that's why we just want to have this molecule to search the third layer first. That is an individual reaction layer to see whether some known reaction has already been synthesized, we can directly use. So the strategy to the search for this layer is based on very common just cheminformatics approach, is a substructure search or similarity search. So once everything has been searched complete, so then we can just adopt all those just the mapped reaction from the third layer to some of the just the temporary queue to store the information for later on use. But if there's nothing has been matched in the third layer, then we can just directly move to the second layer. It's a little bit broader layer, but still has some of the critical function groups we have already captured in this layer. So then we can do the maximum common substructure match. Similarly, we can do substructure search or similarity search based on the backbone of the second layer, which is a maximum common substructure. And in the meantime, we also will do the R group similarity comparison to see how similarity those R groups just between each other. So if this layer has been successfully matched some of the reaction, then we can also adopt into the mapped reaction just the depository. So if there's nothing has been matched, then we can just move to the next layer, which is a reaction center layer, to do the reaction center structure match and R group similarity comparison. So if similarly, if there's something has been, some of the reaction has been matched, then we can dump to the same list. So once everything is done, then we can just come back to this mapped reaction list to see how we can use those reactions to direct the ritual synthesis. So there's a multiple, like once we have that, we just want to pick the most just appropriate reaction to go to this final step. So currently we are just thinking we are using very just a simple approach using some of the reaction metadata, which are available from our database, which is reaction yield, reaction condition, or availability of the raw materials. We can direct it to do the ranking. So once that's it done, we can just go to the direct those ritual synthesis. So this is just the overall picture, how we can just establish those ritual synthesis application on top of this knowledge base I'm just talking about. So now, then I will come back to see how we just come up or develop this knowledge base. So we start from those about more than 100,000 USPTO reaction from the USPTO. And so just allocate by the next move. So this is Gerge helped me to do the allocation by using the next move. So once we have those allocations being done, so next move will help us to just mapping all those USPTO individual reaction to specific reaction class and the reaction just ontology ID. So then we can just better organize all those 100,000 USPTO reaction. And then we have those 68,000 reaction has been allocated, successful allocated, which is corresponding to 54 different reaction classes. So this is a distribution for this 54 reaction classes. For each of them, you can see how many number of the individual reaction corresponding to each of these reaction class. So once we have those allocations being done, then we can start to just play around with those reaction data to establish all those 3 layers. So with that, we have those allocation, those reaction with allocation. So because this is our first pilot study, so we not just want to complex this whole process. So then we just only focus on the reaction with one product. But you can see there's not many reaction with more than one product. So majority of the reaction we have is with one product. So we end up the 66,000 reaction with one product. And we do some of the cleanup to remove some of the just reaction with some of the error smiles. So then we just have those, just the reaction be grouped to the just the 54 reaction classes I mentioned that before. So for each of those reaction class, then we can just directly extract those product smiles as the third layer, which is the individual reaction layer. So once we have that, then we can start to play around with those individual products. So in order to do that, we just want to start to build up the second layer to in order, like I mentioned that before, the second layer is mainly just the maximum common substructure search. So how we can just get those common substructure within just a set of the reactions. So we just plan to do some of the reaction clustering. So for each of those reaction class, we extract all those product smiles, then we just simply using those fingerprint and calculate the tiny motor similarity and use that similarity to do the product clustering. So this is just one simple example to show like this 340 reaction within this particular reaction class. Then we have a just go through this process, we can just have those cluster being generated. Like the first cluster has 12 different reactions, which is corresponding to the individual reaction ID, and so on and so forth. So once we have those cluster being generated, then for each of the cluster, then we can start to extract those maximum common substructure and R groups. So which is our second layer maximum common substructure. I just mentioned it before. So this is the one example from the previous slide. Is I just chose the third cluster, which include the 10 different individual reactions, which is corresponding to this individual reaction with those USPTO ID. And this is a snapshot to show how that's just the information has been structured. So we extract those this particular cluster with the maximum common substructure, which is showing here. So they have a backbone is a reaction, sorry, is a maximum common substructure. The rest of the structure has been represented with a different R groups. And the red circle one is showing this is a reaction center for this particular reaction. So for each of the individual reaction will be represented the way which is, I just mentioned, is maximum substructure in R groups. So which is showing here, like this is their actual products for this particular reaction. So this one will be represented as core, which is a maximum comma substructure. And for rest of them has been represented as R groups, R1, R2, R3, and R5. And referring to these three different just the product, you can see they have a same core, which is maximum comma substructure, but the R groups is different. So this information will be stored for the just later use. So once we have this second layer, then we can move to the last layer, which is first layer's reaction center. So that's why it's very straightforward. So we just use that 66,000 directions without any error or smells, as I mentioned it before. So then we can start to extract the reaction center and R groups. So Yuhong has helped me to just do this kind of the reaction center extraction. So gave me a lot of help on that. So once we have that, then we can just jump that into the first layer, which end up with 53,000 reactions with the reaction center and the R groups. Some of them just have just a problem to process when we do the reaction center extraction. So once we have that done, then we can represent similarly as a second layer. You can see we have the cone, which is the reaction center, and attached to one of the R groups. So once we have these three layers out, then the next question is we are thinking how we can better represent those kind of the information for easier or efficient use to support the ritual synthesis design. So firstly, we just come up those data model to see how we can better represent those information and represent in a graph view. So this is a simple just a data model we have, like say stuff from the individual reaction. So the reaction is belong to one of these reaction class. Right now we call reaction type. And for each of the reaction, they has a product. So then the product has a reaction center and has a maximum comma substructure. So with this very just a simple data model, data structure, then we can just start to pro all this information to the Neo4j, which is a graph database to have the just the interactive just search function to able for us to play around with those data. So this is a very simple example to show you, which is a screenshot I got from the Neo4j. As I say, Neo4j is one of the graph database we just proposed to use. So this is actually reaction type, which has I include in the previous slide as an example, and which has three different reaction belong to this particular reaction type. So like I said, this is just a screenshot, just a demonstration. So now all of them has been attached to this particular screenshot. So only three reaction, individual reaction has been just included. So this is the individual USPTO reaction. And for each
change, sorry, we're within the 5 minutes.
Oh, okay. So yeah, I have one more line, one more slide. So with each of those reaction, we have the product. So the products then have a reaction center. Oh, sorry, has a reaction center and maximum comma substructure. So so you can see how we can store that information for each of these nodes. So the highlight node is a maximum comma substructure, which is still the core structure and the R groups, and also the unique just identifier we just gave to each of these nodes. So yeah, so then I can go to the last I have. So there's multiple things we just want to explore for the next step, especially just to finalize this data model and just expand the current data model with the latest version of the USPTO data. So as I say, right now we only include like say 100,000 reaction, but we just want to expand to the entire USPTO data. once we have that finalized, so then we can start to play around with that to have some of the visual sciences application can be developed on top of that. So there's a lot of things we can do, either just go through like network analysis or some of the deep learning application. So then we can just move to the next step to do the reaction prediction. So now finally, I just want to say we have the just amazing Aspire to make this happen. Thank you so much for your attention.
Thank you so much, Jim, for the excellent talk. And I just would like to say that I'm very excited to start integrating this method into our integrated computational platform. And also, I would like to, as the audience, to ask a question from Chin. We will have probably time for 1 or 2 questions. In the meantime, Chin, I'm wondering whether you have explored your method so that you can systematically extract transformation rules from reaction data set. Can you use your method to do that?
Yes, of course. So I think once we have those, just like I say, all those kind of things is being just loaded right to the Neo4j, then we can just simply search against some of those just even the third or second layer or first layer, right? Then we can just directly extract all those relationships. So that's why this is the reason we plan to use this graph database. All those kind of the association has been linked together. Then we will be able to extract all those just rules, transformation rules being just linking this graph database.
Thank you. And maybe another question is that I'm just curious, what clustering method did you use? And also I'm particularly interested in when you use the Tanimoto similarities, how did you determine the threshold?
Right now, like I say, it's very simple. Just adopt those RDK, those clustering just methods. So they will just generate based on those Tanimoto similarity. They will generate that's just the score. So I will choose 0.8 as a cutoff. Then just have those clustering just being just produced.
Great, thank you so much, Chin. I don't see any questions yet from the chat box. So, and also we're on the time here. So with that said, I would like to thank for all the speakers for the excellent talks and also for the questions and the great conversations. And with that, I would like to conclude our informatics poster session. And I would like to ask everybody to please join the main room. And now I will stop the recording and also we'll close this breakout session. Thank you so much again for attending this session.